we're going to go from current slide. I may even turn on the projector for you today. Feel magnanimous. So, let's go over just a couple of announcements first. Don't forget about your student course evaluations. Some of you, I think, maybe have already done them, I hope. If not, please don't forget to do them. The last date they're open is the 8th of August. Don't wait that long. I'm not going to be here to remind you on the 8th of August to get them done. So get them done sooner rather than later. Okay? But you can wait to see the grade if you want to. But once you do, don't forget to do the student course evaluation. Okay? Now, the other thing is my office hours. We've been working kind of like crazy trying to get ready for a big hearing tomorrow, which is a planning hearing, and it's at 1:30 tomorrow afternoon. So my office hours state that typically I'm here on this campus once Ricky's here on Tuesday and Thursday, 10:45 until around 4, when I would normally go over to the Birmingham East Campus for my physics class. Not tomorrow. Tomorrow I've got to be over on the Birmingham West Campus by 1:30, which means I'll leave no later than 1 o'clock here. In fact, considerably before 1. Now, I may even have to leave earlier than that if some of the people have come up with more documentation. We had a meeting last Thursday, but not everybody had everything there. If they come up with more and I need to put it into the binder, then I may have to go there earlier to get everything put together. So I may be leaving here as early as 11 o'clock. I hope not, but sometime between 11 and 1 I will be leaving. Okay? So my office hours here on this campus tomorrow are pretty short. Okay? Once that's done, though, then Thursday, hopefully, I'll be back on sort of regular things. So I'll be 10:45 until I'm going to, well, I don't have much term left, 2 days perhaps, but probably start leaving at 3:45 rather than 4:15 rather than 4:30, because I found out I can't always count on not getting stopped by a train or traffic or something else, so I'm going to probably start, oh my word, somewhere. I didn't need to try anything. Okay. Okay. This is where we're scheduled to start off. So, except for change of office hours tomorrow, I hope to be back at least on more regular office hours Thursday, and then the following Tuesday. Okay. Corey still hasn't come in. Lance hasn't come in. Nicole has come in. And Jack has come in. So I have everybody now. 1, 2, 3, 4, 5, 6, 7, 8, 2, 4. Got it. Okay. Now, let's see. While I'm thinking of that, let me just mention this. I've gotten the big 3 papers in. Okay, that means I still got the vast majority of the class have not turned in research papers. The first test, there's still 2 people who haven't turned in the first test. One is here and one's not here. Test 2, I've only got 4 in, so still waiting on those. So please, folks, let's get those things caught up because we only have class Wednesday and Monday. All right. All right. Any questions on anything we've done so far? Okay. Bill reminded me what we're going to do at this point. We're in chapter 10, which is conics, parametric equations of polar coordinates. Conics, we just did a quick run through, slideshow on that. Parametric equations, you're responsible for that. Polar coordinates, you're responsible for that, but polar graphs, we're not, so this is just going to be another slideshow here. So polar graphs, where we're starting off, this is on page, it's in section 10.4, polar coordinates and polar graphs. We've done the polar coordinates part. Just do a quick review of polar graphs, slideshow of this, and we'll move on. Okay. Now I hope my battery comes back. Okay. It says, describe the graph of each polar equation. Confirm the description by converting to rectangular equation. Okay? Now, this is a fairly easy one. Okay, now a polar graph, remember how a polar graph looks? I don't mean to do too much on this, but this one's so easy, I want to show you this. On a polar graph, we start out with an XY coordinate system, though we're not going to do that, okay? This is just to give us a reference for our angles theta, okay? And then we'll pick off 1s, 2s, 3s, whatever. And these will be circles, okay? And I wish I could do it gently, but I can't draw circles well at all, and they're getting worse, okay? Let's see if I can get something a little bit better. Okay, let's see if I can clean that up a little bit. That one's a way off, that one's sort of off. That one's not as bad, okay? And then this will be at 3. Okay, something like that. And then you could do your various angles there, 30 degrees, 45, 60. And then do the others in the other quadrants as well. Okay? Now, the first one here, pretty much a piece of cake. R is equal to 2. Go out, 2, second circle, there it is. There's R is equal to 2. And they say confirm it using rectangular coordinates. R is the square root of x squared plus y squared. That's equal to 2. Square both sides. X squared plus y squared is equal to 4. Circle of radius 4. So yeah, that's this. Theta equal pi thirds. That's again a pretty easy one. That would be pi thirds is up like this. There would be theta is equal to pi thirds. Okay? Now, for any value r, even if r was negative, then you could conclude it down here too. Okay? Well, what is theta? Inverse tangent. I said I wasn't going to do too much of this. I'm doing more than I want. This is the inverse tangent of y over x is equal to pi thirds. So this is saying the tangent of pi thirds is equal to y over x. What is tangent of pi thirds? Anybody? Say again? Over 3? I think that's it. So this would be root 3 over 3 is equal to y over x. That would be y is equal to root 3 over 3 times x. And that sure enough would be a line through the origin that has a slope of root 3 over 3, which is exactly what that was. Now, the third one is a little bizarre, so let's just do that. Let me do it in a different color. Pick a color.
Orange.
Orange. Aren't you glad you did that? Okay. All right. So, let's just pick a theta. Easy theta. Easier. 0. Let's 0. 0, 0 would be then, because the, oh, sorry, that's not right, is it? I was thinking that said sine. It doesn't say sine. Okay, so this is probably going to erase way too much. Yes, it did. All right, let me get my, let me get my color back. Okay, go back to orange. Okay. When theta is equal to 0, secant of 0 is, anyone remember? 1, okay? And so r is equal to 1. So theta equals 0 here, there's where we'd begin. R is equal to 1. Okay? Give me another one. You said pi halves before? Okay. Theta equal pi halves, what's secant there? Okay. Undefined, exactly. So can't really do that one, okay? So we're going to have to back up, and this gets tedious. So I'm not going to do any more with this. You'll see it in the book. What it is, it starts here, and as theta, let's just draw the secant function here for a moment. It's 1 over 1 over cosine, and that's how it goes approaching, there's your vertical asymptote there at pi halves minus pi halves. So your secant is getting infinitely larger. Well, without going into gory detail, it just goes like this. Okay? And if you think about it, R is in terms of x and y, see the easy way to do this. Let's do this as 1 over cosine, right? And multiply both sides by cosine, you get r cosine theta is equal to 1. R cosine theta is x equal 1. There's your line, x equal 1. So that's what this one is a vertical line in front of that. That's far easier to do this way than try to plug in values there. You can plug them in, but boy, they become a pain in the neck, okay? Or some other body part. Okay. So, as you see, there are some very simple polar graphs you can do, and after that, they get incredibly tedious very quickly, or they can anyway. Okay? So, let's just see quickly how they do. There's the first one. R is equal to 2, circle of radius 2. And x squared plus y squared is equal to 2 squared in rectangular equation. Okay. The next one, theta equal pi thirds. That means all along here, when theta equal pi thirds, you just up and down that line, positive and negative. So there we have that one getting in rectangular coordinates. That would be, and there they have tangent theta is y over x, so y is equal to, we say root 3 over 3, it's just root 3, sorry, root 3x. Okay. And then the next one is this one, and to draw it is miserable, but rewrite that as r cosine theta equal 1, that's x equal 1. So write it in rectangular coordinates. Draw or graph it in that. Much easier than trying it the other way. Okay. Now, here's another one. Fairly strange. The graph of r is equal to 1/2 theta is shown here. It was produced with a graphing utility in parametric mode. That equation was graphed using parametric equations. And this is why we're not going to do this section. That gets miserably complicated really, really quickly. Okay, I don't even want to go into this. How to get from this to that enough is a pain in the neck. So this is going theta varying from minus 4 pi to 4 pi, and it's not even completely obvious where you start. I guess if you start at minus 4 pi, let's just think theta of that, that would be minus 1 pi, 2 pi, 3 pi, 4 pi. So this must be where we're beginning. And if you plot along here, it goes this, that gets you back to theta equal 4 pi. Okay? That's the spiral of Archimedes, by the way. He had too much time on his hand, I'm afraid. Okay. Pretty incredible, the polar coordinates, and the fact that Archimedes was doing things like this back how many 100 BC. I mean, that's pretty incredible. Don't worry about this, you're not responsible for it. But this is, polar graphs can easily get very complicated very quickly. All right, now, they have a little bit here on slope and tangent lines, and again, let's just hit the high points here. To find the slope of a tangent line to a polar graph, consider the differentiable function given by r is equal to some function of theta. To find the slope in polar form, use parametric equations, and the x is going to be r cosine theta, which r being alpha theta times cosine theta, and that's basically how they got that previous one. And y is equal to r sine theta, which would be your alpha theta sine theta, which is basically how they got the other one before. And if a smooth curve C is given by the equation x equal f of t, y is equal to g of t, then the slope of C at xy is dy dx, dx dt over dy dt over dx dt. Hopefully you remember we did this back in in parametric equations. We had that. Now this is as long as the dx dt is not 0. Using the parametric form, dy dx given by here, okay, you have dy dx is equal to dy d theta over dx d theta. But dy d theta, go back last slide and plug those values in, and it was a product rule. The first time derivative of the second plus the second time derivative of the first, that the numerator and denominator, and you get a form that looks like that, which is bad enough, and that leads to this. If f is a differentiable function of theta, then the slope of the tangent line of r is equal to alpha theta at a point r theta, then that's your formula. That thing we had on the last one, here it shows up again here. Provided the dx and theta is not 0 at any r theta in the deal. So your tangent line then would be at any value r theta, say this is part of a curve there. The tangent line here would be given by this formula here. What a joy, huh? Don't sweat this. You're not responsible for this on your test. But just in case you ever need it, you've seen it, hopefully you can use it, go back and access it if you need it. Okay. Now, to get the places where dy d theta is equal to 0, then you just set that numerator, as long as the denominator is not 0, set the numerator equal to 0. And the solutions for this would be the case, equal 0. Those are going to be your vertical tangents, okay? Because remember, you can't have that equal 0. That would be a horizontal asymptote, basically, which would be a vertical tangent. So If they both are simultaneously 0, no conclusion can be drawn about the tangent line. So, again, you're not responsible for it. Let's just move on. Let's just see how they do this. This one's a fairly simple one, so to speak. Notice it's only between 0 and pi that we're dealing with. Begin by writing the equation in parametric form. X is equal to r cosine theta, which r is sine theta, so it would be sine theta cosine theta. Your y is r sine theta, which would be sine theta sine theta sine theta, sine squared theta. And then differentiate both x and y with respect to theta, set each derivative equal to 0. The first one, the dx d theta, that's this one. That would be cosine squared theta minus sine squared theta, which is, by the way, cosine 2 theta, and that's equal to 0. When that is equal to 0, your theta is pi fourths or 3/4 pi. Do the same thing for the dy d theta. That would be 2 sine theta cosine theta, because remember it was sine squared theta, so its derivative would be that, which happens to be sine of 2 theta, and that's equal to 0 at 0 and pi halves. They're not simultaneously equal to 0, so you have your horizontal and vertical tangent lines, and there they be. And I'm not sure I recognize that as a circle to begin with, but it must be, because those are your horizontal and vertical tangent lines. Okay, so you see you can continue doing this kind of stuff. Find the horizontal and vertical tangent lines of the graph of this one, where you're going from 0 to 2 pi. And sort of would be helpful if you could see the graph first, but they're not doing it that way. So y is equal to r sine theta. Plug in that r and differentiate with respect to theta. There's y is equal to r sine theta. Plug in that for your r, and you get, boy, have they skipped some steps here. You get this thing times sine theta. Oh, and yeah, that's all they did. They plugged in this times sine theta, and then take a derivative with respect to theta. And boy, what a pain in the neck that is. Once you get that, set it, let's see, we'll multiply through, okay. And just to let you know what they have done here, they multiplied, and then they did this last one and changed it 1 minus cosine squared theta. So you get everything in terms of cosine. Now, that's the rationale for doing that, and that gives you this form, which you can pull out a common factor of 2 then. It's hard for me to read from here. And then that does factor, and you get the places where dy d theta is equal to 0, and they give you where cosine theta is -1/2 or equal to 1. So there are the values. Theta is equal to 2 pi thirds, 4/3 pi, 0. Okay. When you do the same thing for x, plug in what r is, and you get that. Multiply through, and you get that. Take a derivative, you get that. Set it equal to 0, or you will set it equal to 0, and then factor it, factoring out the sine 2 theta. Now this one you don't have to do anything, because these factors, this is all in terms of sine, that's all in terms of cosine, so you can just solve that as is, and that gives you theta equals 0, pi, pi thirds, and 5/3 pi. Now, just as a reminder, 0 showed up in both of those, right? Yeah. So 0 is off limits. You can't say anything about when theta equals 0. But the 2/3 pi's and 4/3 pi are here, and 1/3 pi, pi-thirds, and 5/3 pi are here. So you can say something about these three and the 2 from there, but you can't say anything about 0 because they were simultaneously 0. Okay. From those results from the graph shown, you can conclude that the graph has horizontal tangents at the 3 2/3, that's there and there, and vertical tangents at here, here, and here, even though that's the same representative. At theta equals 0, you can't tell, and sure enough, that's a cusp there. It has one value coming in this way and another value coming in that way, so you can't really tell. It looks like it could be close to horizontal tangents, but you just can't tell. And that, by the way, if you picture it, looks a little like a heart, and they call it cardioid. Some sort of strange name. Okay. Notice both the derivatives are 0 when theta equals 0. Using that information alone, you do not know whether it's horizontal or vertical tangent line, but from the graph you see it's a cusp there, and they appear to be horizontal, the tangent lines. Okay. I just don't think it's worth spending lots of time here. Let's look briefly at some special polar graphs, and because you will see, I don't know if you will, but you have potential of seeing some of these somewhere in the future. First of these are called limicons, I think is how you pronounce that. This is a limicon with an interior loop. This is a cardioid, which is another one, facing the opposite direction from what we had before. This is a dimpled limicon. Y'all are too young to remember the dimpled chads in the Florida election back in Bush v. Gore, but that's not the same one, but it has something like that. And this is a convex. I'm not quite sure why they call it convex. It almost seems like it's flat there, but it is a different kind of limicon. Now, this is the general formula for it: a plus b cosine theta and a plus b sine theta. And it depends on the ratios, plus or minus b sine theta. So you can get those various ones there. Okay. Other are called your rose curves. These have petals to them. They look more like daisies than roses to me, but anyway, they call them rose curves. When the end petals, when n is odd, 2 end petals when n is even. So this will be n equal 3. Wherever you start here, go up, around, there. So n equal 3, you get 3 petals. N equal 4, you get 8 petals, twice as many. Starting here, you go this one to that one. I can't follow it exactly, but you wind up with 8 petals before you get back. N equal 5 is back to 5. N equal 2 is down to 4 rows. These are circles with lemniscates. Now, I don't know if any of you have had much chemistry yet, but this is beginning to look like the lobes on your quantum numbers. So I'm not sure they follow the same pattern, but at least it's beginning to look that way. So don't sweat these too much. Circles are like this, the lemniscates like that. Okay, whether it's at an angle or not depends on whether it's sine or cosine. So even and odd, you can think of it that way. All right, that's it. Okay, that's 10.4. Don't worry about anything else in that. The first part of 10.4, when it's talking about polar coordinates, we already made those assignments. These with polar graphs don't sweat them. Okay. Now, can't remember. Did I say we do a quick PowerPoint show of 10.5 as well, or were we going to move on? I don't remember what I said. I'm just about in favor of just moving on because I really think 11 is more important to you than 10.5. 10.6, interesting stuff, polar equations and conics with Kepler's laws, and Kepler came up with these laws pretty much empirically, which was pretty interesting. How for some reason it may come back. But anyway, he had these three laws of gravitation, of planetary motion, and incredible how he came up with them. But let's not do anything more. But easily you can see a good paper topic in, or more than one in those. And that's all we're going to do in 10. Let's move on to 11, because we are running rapidly out of time. So let's go down to 11.1. And your last test will be the 2 sections, I believe it was, in 10. No, I'm sorry. What was it? 9? Yeah, we did sequences and series, those 2 sections, and then in 10, 10.2, 10.3, and the first part of 10.4, polar coordinates. And then chapter 11, whatever we get to cover here. And I'll try to, but with this mess of a hearing coming up tomorrow, I don't know if I'll get the test made out in time for Wednesday morning, for me to give it to you on Wednesday. I'll try to get that done, but if not, I'll get it to you Monday, and just get it back to me anytime next week, Monday, Tuesday, Wednesday, or Thursday. But let's see what we can go with it. All right, and for some reason my slideshow acts like it's not coming back, but let's just see if it will when I do this. Yes. I don't know why. Okay. All right, vectors and the geometry of space. 11.1, vectors in the plane. Okay? Now, some of this is incredibly easy stuff. So I think you'll find this is very nice to have on your last test. Okay? I take it several of you have had physics. If you have, you've probably eaten up vectors by now. If not all of you have had physics, this will help you when you get there. Objectives are to write the component form of a vector. That is the way to write a vector, okay? The component form is the best way to do it. To operate with vectors, use component form. We'll perform vector operations and interpret the results geometrically, which is sort of a pain in the neck sometimes, but sometimes it's instructive just so you see it better. We'll write a vector as a linear combination of standard unit vectors, which is just another way of writing it in component form. Okay? So, what do we mean by component form of a vector? Many quantities of geometry and physics, such as area, volume, temperature, mass, time, are mainly scalar quantities. That's all they are. And area is how much of a flat surface you got covered, or some sort of surface. Volume is how much is contained in a three-dimensional description. Temperature, it's a number. It's just a number. There's no direction associated with temperature. Mass, same thing. How much of an object there is, there's no direction associated with it. Time, you might say, forget about Back to the Future. No such thing. That's Hollywood. Okay, so time just is a number. It doesn't have a direction associated with it. Now notice I didn't say quite as much about area because there is a sense that if you have, say, a plane here, you could talk about, well, the area with a direction this way or that way. We'll get to that later, but generally the area itself is just a number, and the volume is just a number. Anytime you only have a numerical value, it's called a scalar quantity, okay? The real number associated with each of these is called a scalar. What we used to call real numbers, now we'll be calling scalars. Other quantities, and I like to start with velocity first, acceleration, force, goodness gracious, well, I'm going blank. Momentum, goodness gracious. Other things such as that have both a magnitude, scalar type characteristic, but also a direction. Velocity has to be going somewhere. Speed doesn't, okay? Now notice they didn't mention speed up here. Speed's a scalar quantity, velocity is a vector of the vector quantity, Acceleration, a vector quantity, always associated. A force is associated with acceleration, it's a vector quantity. A momentum is associated with a velocity, so it's a vector quantity. They have both magnitude and direction, cannot be characterized completely by a single real number. You have to have some other descriptor in it, as in a direction. So, what do we mean by one of those quantities? Here's one. A directed line segment is used to represent such a quantity. Now, directed line segment. Directed means the direction is there and is important. Line would indicate infinite in either one of two directions. Line segment, finite. So therefore it does have a magnitude, okay, a real number part, but it also has a direction. Now, these directed line segments, you have an initial point, typically named P, and a terminal point, typically named Q. So you could name them other things if you wanted to. When you represent these with a little arrow over it, if this was just a line segment with no direction associated with it, we'd put PQ or QP. It wouldn't really matter, because then all you're talking about is the magnitude between those. But with a direction associated, the first letter given is always your initial point. The second letter, the one that's under the arrow, that's your terminal point. So the initial starts here, goes there, so the arrow is in the direction of the Q. Okay? The second letter listed. Now, a directed line segment PQ has, okay, we already said initial point and terminal point. Its length is called its magnitude. That's the real number part, and the direction has to do with where it's heading. We'll get to that later. Directed line segments that have the same length and the same direction are called equivalent. Later we'll actually use the word equal, but right now we'll use the word equivalent. So if all these vectors here are directed line segments, have exactly the same magnitude, and are exactly parallel to each other, meaning same direction, they are equivalent directed line segments, which later we're going to call vectors. Now, what would happen if you turn one this way? Exactly parallel, exactly the same magnitude, but going in the opposite direction, so that would not be equivalent. Everything else would look the same. The arrow would just be pointed in the opposite direction. So the set of all the directed line segments that are equivalent to a given directed line segment PQ is called the vector in the plane, and is denoted by V is equal to PQ. Now, in this notation, remember, the initial point was P, terminal point was Q, the arrow is pointing from P to Q. In this notation, that's a bold V. I don't write bold, okay? I can't write bold. You wouldn't be able to tell if I was writing bold or not bold. So when I write the V, I put the arrow over it just like this. It's just that it doesn't have an initial, it's just that the arrow will be there, indicating that is a vector. one more little variation on that theme, but we'll get to it later. In typeset material, the vector is usually denoted lowercase, boldface in typeset, such as UVW. Okay? When written by hand, however, that's when we put the arrow. Now, quite often my arrow will only have one wing on it because I'm lazy. I don't put two wings with it. You'll see that there was a wing magic there. Vectors often described by letters with arrows above them. But notice here, there's no initial and terminal, so it's not as important. That's just a vector U, vector V, vector W. With this one, that's the initial point, that's the terminal point. Okay. And this is usually just a single arrow. Mine quite often have single wings also. Now, be sure you understand that a vector represents a set of directed line segments, each having the same length, same direction. In practice, however, it's common not to distinguish between a vector and one of its representations. So if you want the vector to be right here, you just draw it here. If, however, you needed it down here, as long as it's the same direction, same magnitude, you can draw it anywhere on the page you want to. And we'll see that very, very soon. So it's common not to distinguish between talking about a vector or one of the representations of the vector. We always call it the vector. So, here's example 1. Let V be represented by the directed line segment from 0, 0 to 3, 2. Okay? So, I don't draw grids very well. Let me do at least a semblance of one. Okay. Okay, let's just imagine those are evenly spaced. 0, 0 is the origin, and 3, 2 would be 3 on X, 2 on Y. Y'all are familiar with that, right? So there would be, why this does that, I don't know. So there would be the 2 points. Now, this gets into another kind of aggravating detail, okay? In this book, so far, and I think throughout the book, when you see parentheses, that means points, okay? Open parentheses, X coordinate, Y coordinate, close. So these are coordinates of a point, okay? Later, we will see vectors are represented by something very similar to it, but they have angle brackets, not parentheses, okay? Now, back when I was young, and Bill, maybe, I don't ever remember angle brackets. That was something that's come out since then to now, okay? But this is the aggravating part. I like this author, okay? And we use his text for pre-calculus, algebra, and trig, and he used this notation I'm just describing. We use his text for calculus, and he uses this notation, I think, throughout this book, too. I use a text by him for linear algebra, and he uses parentheses to represent his vectors. And it drives me nuts because I'm used to everywhere that if it has parentheses, point, these are coordinates of a point, x, y coordinates. Later we'll see components of a vector. Those are inside the angle brackets, unless you're in his other book, okay? And then they're not. So it's going line segment from 0, 0 to 3, 2, then put your arrow toward the 3, 2. This is the point down here, 0, 0. This is the point up here, 3, 2. Okay. Now this is the vector V. So label it V. I can't write bold, so I put the arrow over it. Single wing, but still an arrow. So let's do U be the vector directed by 1, 2. 1, 2, that starts right here, and it goes to 4, 4. That would be 1, 2, 3, 4, 1, 2, 3, 4, somewhere about there, okay? And again, my scales are pretty lousy. Everything's pretty lousy. So this is point 1, 2 to point 4, 4, in the direction from initial point 1 to terminal point 4, 4. Now, they shall say, show that these are equivalent. What does it take to be equivalent? Two features. One feature, same magnitude. The other feature, same direction. Okay. So let's deal with magnitude first. How do we do the magnitude or the length of a line segment? How do you get a length of a line segment? The square root of what you say, difference of x's and y's? Yeah, it's the square root of the squares, okay? So this would be, say, x2 minus x1 squared plus y2 minus y1 squared, okay? And that would be, in this case, if your x2 was say this one here, 3 minus 1, that would be 2 squared plus 2 minus 1, 3 minus 0, I can't read. 3 minus 0 would be 3 squared minus 2 minus 0, plus 2 minus 0 would be 2 squared. This would be the square root of 9 plus 4 equal the square root of 13. Okay, let's do this one up here. The square root of x2 minus x1 squared plus y2 minus y1 squared. What would that be? x2 minus x1, 4 minus 1 is 3 squared, plus 4 minus 2 squared is 2 squared. You don't have to go any further. You see that's exactly the same length. Exactly the same length. Therefore, are they equivalent vectors? No, we don't know that unless we know their direction as well. We have to know direction. Now, how can we tell direction? The slope of the line. And what is the slope of the line? Yeah, change of y over change of x, which would be, like you were saying, y2 minus y1 over x2 minus x1. Now notice these were the same quantities we just showed here, so let's go back and get them. The change of y's was 2, and the change of x's was 3. Let's go up here and see what we get. The m, which is the delta y over delta x, this would be 2 over 3. Well, they were the same things here, so they've got to be. So yes, not only are they the same magnitude, they have exactly the same direction. Okay? Now, can you always just look at that? Not quite. Okay? Because if one of these had been done like this is the initial point in that terminal, that part would look exactly the same. But the delta y or delta x, because you squared them there and they look the same, this one would be the opposite of the other, meaning the negative of the other. So you do have to actually do a little more work than I did here. Okay. Does that make sense mostly? A little bit? Vaguely? Okay. So let's erase that and see what we got. If P is the initial point, Q is the terminal point of V, there it's shown there, almost as pretty as mine. R is the initial point. S is the terminal point of the second one. U, there it is. They're shown there. They sure look equivalent. How you show they are, you can use the distance formula to show they have the same length, which is exactly what we did. PQ was 3 minus 0 plus 2 minus 0, both of those squared, added together, take a square root of 13. RS, 4 minus 1 squared plus 4 minus 2 squared, exactly the same numbers, 3 squared plus 2 squared, square root of 13. Okay? I can't believe, oh, there we go. It's losing its mind, I think. Okay. Okay. So we got both of those. Both line segments have the same direction because they're both directed toward the upper right on lines having the same slope. Now, they didn't show you the slope, but they just said it from the picture. But if you look at rise over run, you see they are the same slope. So they sort of skated by with that one. Oh, here they have it. So they do it. Rise over run, 2 over 3, 2 over 3. Okay? So the slopes are exactly the same as well. All right. Now, because PQ and RS have the same magnitude and the same direction, okay, you can conclude the two vectors are equivalent. Therefore, V and U are equivalent vectors. Later, we'll call those equal. And is it my imagination, or is that a different size than that? I don't know. It doesn't really matter, but it just looks bizarre there. Anyway, the directed line segment whose initial point is the origin is often the most convenient representation. To put the initial point at the origin and go from there. And we'll typically call that the standard position. Okay? This is the same vector, an equivalent vector as this one. This one's the standard position, that one's not. There are times we want it in standard position. That's the easiest thing to do. There are other times we want to translate it somewhere and we may want it in some other position. So, but they are equivalent. Okay? So this is what we say, the representative vector V is called the standard position. A directed line segment whose initial point is origin can be uniquely represented by the coordinates of its terminal position. Okay? The point Q, V1, V2, because if you had translated that other one U down here, you would have exactly that same terminal point. Okay? Because it have the same initial point too, and they're the same vectors. Okay, so now we're getting toward what we mean by component notation, component form of a vector. In the definition, note that the difference in notation between the component form and the point. And this is crazy. This point, if that's a point, those should be parentheses there. Okay, let me see if they got that wrong in the book as well. Yeah, in the book they got it right. If that's a point, these are parentheses. Okay, if it's a vector, then it's angle brackets. Okay, they got it right in the book, wrong on the slide. All right, but they look almost identical. These are components of a vector. These are coordinates of a point. Okay, the words sound similar, components and coordinates. They're different. Components are the characteristics of a vector. Coordinates are the characteristics of a point. So the definition of a component form of a vector in the plane, if V is a vector in the plane, whose initial point is the origin, standard position, and whose terminal point is V1, V2, the component form of that vector V is V1, V2. The difference here being the angle brackets here for a vector, the parentheses for a point. Coordinates V1 and V2 are called components of V, coordinates of the point. If both the initial point and the terminal point lie at origin, this is weird. It messes up everything, but it's absolutely necessary. The vector is called the zero vector and is denoted by a bold 0, meaning it's a vector with components 0, 0. Now, why do I say it messes up everything? But it's absolutely necessary. What is the magnitude of that vector? 0. Okay, so it has no magnitude. What's the direction of that vector? It has no direction. How can a point have a direction on it? Okay, it can't. So therefore, it almost fails to fit the definition of a vector, but we have to have it. And why do we have to have it? So we have a linear system. Our vector system has to be linear. You have to have the 0 value. Okay? And everything, you have to have a 0 value. So we have to have a 0 vector, even though it means almost nothing. I mean, it's nothing. Okay? That definition implies two vectors, U1 and U2, which are U1, V1, U1, U2, and vector V, V1, V2, are equal if and only if U1 is identically the same as V1, and U2 is identically the same as V2. Okay? The only way two vectors are equal. So what we were calling equivalent, now we're calling equal with this definition. Okay. Now, the procedures listed below can be used to convert directed line segments into component form of a vector and vice versa. So what if we have a directed line segment from point P, P1, P2, point, parentheses here, to point Q, coordinates of the point Q1 and Q2, in parentheses, are the initial and terminal points of a directed line segment. Then the component form of that vector, V, that's represented by PQ, is V1, V2, where V1 is final minus initial, comma, final minus initial. Always. And remember, I sort of snuck in, but we should be familiar. Delta is always final minus initial. Delta meaning difference, subtraction, minus initial. Final minus initial. Can't talk. So it's Q1, the final x coordinate of this one, minus the initial x coordinate of this one. That's the x, or the first component of the vector, and then Q2 minus P2, second component of that vector. Moreover, from the distance formula, you can see that the length, or the magnitude of that vector V, is the magnitude, the difference here squared plus the difference there squared, which is merely V1 squared plus V2 squared. Magnitude of a vector is then always the square root of the sum of the components squared of that vector. Now, so far we're only talking two-space, plane, two-dimensional, okay? Later we'll get into 3 dimensions and you'll have 3 components, so you just add another component to it. But right now we're talking about vectors in a plane, which are only 2-dimensional vectors, so we only have 2 components. So by looking at their components, you can see the magnitude, you can see the direction, okay? Because everything's given by those components. And that's why I said when we have the other 2, as soon as you got one, you have the other. All right, number 2. If V is V1, V2, this is the vector, angle bracket, these are components of the vector, then V can be represented by the directed line segment in standard position from P, standard position. The P is always at the origin, and the terminal point is at these coordinates for P, components for the vector Q. Now, right now, you can see they wrote these in italics and these non-italics, or something, or maybe this is serifs and that's without serifs. I don't know. Don't worry. I can't write that way, and they're not going to be consistently that way. So don't sweat that either. Okay. Now, the length of V is sometimes called the norm of the vector V. Okay. Now, if this magnitude or length or norm of V is 1, then V is called a unit vector. Okay. Now, the magnitude of V is 0. Only way that could be if V is a 0 vector. The only way it could be. So that's that. So again, the 0 vector almost to me is a misnomer, but we have to have it. Okay. Now here's where my other deviation comes. I can't write bold, so if this is any old vector V, then I write it like that. If this vector V happens to be a unit vector whose norm or magnitude or length is 1, then here's how I write V. I like to designate a unit vector with a caret on top rather than an arrow. That's so I can remind myself that's a unit vector, okay? It's nothing that's absolutely required, but I will always try to do that just because it's my way of reminding myself that's a unit vector, okay? Now Now, just because I don't do it doesn't mean it's not a unit vector, but I always try to do that. So when you see me do it, that indicates at least I think it's a unit vector, just for future reference. I have a bug crawling across my screen. Okay. So, before we get to vector operations, they're skipping example 2, so let's go back and see if we can do example 2. I guess this is the best place to do it. Find the component form and the length of the vector v that has initial point, okay, vector v has initial point, I'm going to call it P because we've been calling it, of 3, -7. That's a point because it has parentheses there. And a terminal point, we've been calling that Q, so I'll continue calling it Q. It's a point, so it has parentheses of -2,5. Okay, and what two things it said? Find the component notation, component form of that vector. So how would you write V in component form? It's pretty easy. What would it be? Anybody? Don't be shy. It's easy. Okay. Okay. Start with the x component. Final minus initial. Terminal minus initial. Okay. So it'd be -2 -3. Right? And then what would be the second component? 5 plus 7. 5 minus a -7. So this would be -5, comma, 12. Perfect. Okay? Now, that was the component form. Next is the length. What symbology do we use for length, or magnitude, or norm? The double bars of V is equal to what? Square root of what? You could go back and say that, or since you've already found that, just say -5 squared plus 12 squared. Since you've already done the work there, but you're absolutely right, you could do -2 minus -3 squared, 5 plus 7 squared, but there you've already done that, so this would be what? The square root of? Anybody? 25 plus 144, which is square root of 169, which is 13. That happens to be, you're familiar, I hope, with 3, 4, 5 being a Pythagorean triplet. Another one of these is 5, 12, 13. Okay? There's many of them, I guess an infinite number of them, but that's another one. So as soon as you saw 5 and 12, you could almost go to it and say 13 then. So that's its magnitude, or its norm, or its length, whatever you want to call it. A scalar quantity, by the way. The component form, of course, is going to be a vector quantity. Okay, any questions on that? Again, this is pretty easy stuff, right? Okay. All right, now to our vector operations. What are our scalar operations that we're most familiar with? Adding, subtracting, multiplying, and dividing. We're going to right now deal with adding and subtracting and one type of multiplication. That's all we're going to deal with at first. These will be our operations. Okay, so vector addition, which is fairly close to vector subtraction, so we'll talk about that separately, and scalar multiplication. Okay? So here's going to be u, a vector u, bold here. I would have an arrow over it. In component notation, u1, u2, standard way to write it. In vector v, a vector, angle brackets, v1 and v2. They're both vectors. C is a scalar, a real number, just any old number, no direction associated with just a number. Okay? The vector sum of u and v is just, and again, the most important form to do vectors is the component form. You just add the components. u1 plus v1 is the first component of that. u2 plus v2 the second component. So add the first components here, comma, add the second components here, put them in angle brackets. There is your vector sum. I think you could probably imagine what would be the difference. u1 minus v1, comma, u2 minus v2. Okay? The easiest way to do it. They're going to show you other ways. This is the easiest way to do it. Now, the scalar multiple of C and a vector u is C times u is merely that. If you picture, I wish they had done it, C times the vector, angle bracket, u1, u2, with a comma in between there, distribute the C across. cu1, comma, cu2. Okay? That's it. It's just distribute across to each component. Okay? And that these are components, and that is a vector 2, so you still have an angle bracket. Okay? Sum of two vectors is a vector. Scalar multiple of a number with a vector is a vector. Now, while we're here, let's just do the negative of a vector. The negative of vector v, basically that's negative v, which is negative, v1, v2, which would be negative v1, comma, negative v2. This negative 1 would be a constant number distributed across both components. That's it. It's pretty simple. Now, with that in mind, just like we did the sum, the difference of signed numbers would be the first number, add to that the opposite of the second number. Same thing here, to do the difference of two vectors, add to one vector the negative of the other vector. So u minus v would be u plus negative v, which means the opposite of v. So that would be u1 minus v1, just like we said before, comma u2 minus v1. It's that simple. I'm sorry. I wish I could make it harder, but I have to figure out a way to do something. Okay. Just that simple. All right. Any questions on those? Now, they love this geometric, okay? Geometrically, the scalar multiple of a vector v and a scalar c is that vector that is exactly the absolute value of c times as long as v, shown here, okay? But they're leaving something out, okay? Okay. Here's vector v, okay? That's where we start. 1/2 of v would be exactly the same direction of v, but half the magnitude. So whatever the direction of v, exactly the same. 2v would be twice the magnitude. So that's what they're saying, is the absolute value of c times as long as v. So 2v would be twice as long, but exactly the same direction. However, negative v, just like we said, is the same magnitude, but opposite direction. So if this was this way, this one's that way. Exactly the same slope, but the arrow's on the opposite end. Exactly the opposite direction. Negative 3/2 v would then be the negative flips the direction, but parallel, and 3/2 then expands the magnitude by 1.5 times. So that's what we mean by scalar multiplication. Don't ever lose the direction. Well, let's see. I won't say direction. The parallelness of the vector. They're always going to be parallel. It's just the the magnitude changes, and possibly the direction, whether it's a plus or minus in front. If C is positive and C has the same direction as V, if C is negative, then you have the opposite direction. So that's why this part didn't quite say it all, you need this part. Hopefully that's pretty much like you would expect it to be, right? Okay. Now, when you're doing the sum of two vectors, by all means use component notations and add them together. But if you're doing it geometrically, which they love to do, you position the vectors without changing their magnitude or direction so that the initial point of one coincides with the terminal point of the other. Sometimes it's called head to tail and tail to head, that kind of thing. So here's vector V over here, not quite in standard position. Vector U is over here, definitely not in standard position. What if you're going to add those two together? Well, it just depends on which one you start. If you start with U, then take V here and put the initial point of V on the terminal point of U, keeping the magnitude the same of V and the direction the same, and then draw the vector from the initial point of U to the terminal point of where V became. That's your sum vector. Okay? The hard way to do it, but that's exactly what it represents. But it didn't matter. You could have taken V first and then take the U and move it without changing magnitude or direction to the initial point of U from the terminal point of V, and then you get the same vector. Not quite in the same location, but everything else is the same. That's U plus V. Okay? So move the initial point of V to the terminal point of U, and then connect the initial point of U with the terminal point of V, or move the initial point of U to the terminal point of V, and then go from the initial point of V to the terminal point of U. You get the same result. Okay? Now, it's not in the same location, but remember they don't have to be. As long as they have same magnitude, which they have, same direction, which they have, they can be anywhere in the plane. Okay. Now, that vector, U plus V, is sometimes called the resultant vector. Okay? The result of the adding of those two vectors. And they say it's the diagonal of the parallelogram having U and V as its adjacent sides. Okay? So sometimes they call this, rather than whatever I was just calling it, they call it the parallelogram method of adding vectors, which is a hard way to do it. Okay? This figure shows the equivalence of the geometric and algebraic definitions, vector addition, scalar multiplication. Okay? And again, this really gets tedious, but here, you see why the component notation is the way to go. So let's say we had U and V both in standard position, and we're wanting to add the two. Well, you either have to translate U to here or V to there, but you get the same result, obviously. But look at what's going on here. Here is your V1, well, here's your U1 here, that little length here. Here's your V1 here, that component of V that's in direction of the horizontal axis here. We haven't talked about that, but V1 plus U1, and that gives you your U1 plus V1 here. And here's U2 here, and there's V2 here, and you add, it doesn't matter which order, U2 to V2, and you get the second component here. So, component notation, that's the way to go. Okay? Now, obviously this is referring to the points where these are the scalar values of your components. Okay? If these were the vector values of the component, then you would have a vector with angle bracket there. Now, scalar multiplication, on the other hand, if you had U here and you're multiplying that by K, and K is a number larger than 1, then you're scaling up the same vector, same direction, same everything, except you're scaling up this magnitude this way. Okay? However, if k was less than 1, you'd be scaling it down. It would still be the same. And if k were negative, it would be going in this direction, either longer, shorter, or whatever. Now, as if, in my mind, they would have been very fine just to leave it right there. But then they like to show the representation of vector subtraction, which I do exactly by the thing. If this is vector u and that's vector v, if you're doing u minus v, draw vector u and then draw the opposite of vector v and then connect the initial here and the terminal there. Okay. Now what they like to say is this is the result here, but it's also the result here. And I have to sit down and do it. Easy way to do it, by components. By all means, don't get tied up in your parallelograms and other things like this. They can so easily get you confused. Just do the difference of their components. It's just the easy way to do. Now, I know it's awfully near the end of the term, but here we have two people on adjacent pages, William Rowan Hamilton. Some of the earliest work done with vectors was done with this Irish mathematician. I think I've read before they consider him probably the top Irish mathematician maybe of all time, and they place him right up with the Scottish physicist James Clerk Maxwell, spelled like it's clerk, but you know, the Scots don't know how to spell. Okay, they built on each other in some senses. Maxwell built on Hamilton's work. Now, and I'm not sure on this, have any of you done much quantum mechanics? Lucky you. Okay, but if you do, you run into something called the Hamiltonian. And I think it must be named after the same Hamilton, even though he was way before people were even thinking about quantum mechanics. But some of the mathematical things he did must have lent themselves to talking about that. The second one listed here, and this is after example 5, but I want to mention her since I'm mentioning Emmy Noether. Okay, one person who contributed to our knowledge of axiomatic systems was the German mathematician Emmy Noether. She was generally recognized as the leading woman mathematician in recent history. Now, here's something I've heard. I believe this has been documented. When this little known physicist had a problem with math, who did he turn to? Emmy Noether. Now, what was his name? Oh, Einstein. That was it. Albert Einstein. When he had trouble with math, abstract algebra especially, this is who he went to. Okay? She was good. Did she ever get her doctorate? No, she wasn't even allowed, in some senses, to attend classes, though she did. Sort of on the slide, on the sneak. Professors recognized her brilliance and let her sit in. She ultimately came to the U.S. and they granted her, I think, a doctorate. They may have called it honorary, but it was well deserved. Now, of course, why she came to the U.S., same reason Einstein came to the U.S. Yeah, Hitler, Nazi Germany. She was either Jewish or half Jewish. He was too, one or the other, and so they both fled because obviously they were inferior. Yeah, right. Okay. But anyway, enough said there. Fascinating characters, and the sad thing is, it seems like it was an appendectomy or something almost that simple. She died on the operating table. Just some really weird complication. Otherwise, she'd have been probably even more famous as a mathematician. All right, let's do example 3. Here's a vector v, -2, 5, angle brackets, vector components, and vector w, 3, 4. Find each of the following vectors. What in the world would 1/2 v be? Can anyone just write it down? -1, comma 2.5 or 5/2, either one. Okay. How about W minus V? Anyone think of how to write that one down? 5, comma, second, -1. Perfect. Y'all are good. Okay, how about V plus 2W? Okay, V plus 2W, 4. That works. 13. Excellent. Any questions on those? Pretty straightforward. Component notation's the way to go. Any of you drawing your parallelograms? Yeah, you did? No, I hope not. Okay. Use component notation. Adding, subtracting, multiplying the components. That's the way to go. Okay. Any questions on those? Let's just see how they did it. I bet you they do it a little more detailed than what y'all just did. But if you understand it, go for it. The first one, 1/2 V, would be just 1/2. Fine to do it this way. Bring the 1/2 inside the vector. And 1/2 of -2 is -1. That's what I did in my head. And 1/2 of 5 was 5/2. Perfect. The V one, write down 3 minus 2 would be 5. And 4 minus a 5 would be a -1. That's what they ultimately did. I got 5 minus 1. Good, way to go. And then the third one, V plus 2W. V, well, they first said 2W is 6/8. V plus that would be -2, 5 plus 6/8. You can do it that way. It's fine, or you can do it just as you read it. That would be 4, 13, just like you said. Good deal. Any questions? Just a little more detail of how they put it together. All right. Now, here's the theorem. Properties of vector operations. Get carried away here. U, V, and W are all vectors, bold, so therefore they're vectors, in the plane, meaning 2 dimensions, 2 components each. C and D are both scalars, any real number in the world. Okay? Here is the commutative property of addition of vectors. I wish they wouldn't just say commutative property. Commutative property of addition of vectors. If you add, and we saw this in the parallelogram method, U plus V is exactly the same as V plus U. Doesn't matter which order you add vectors, they come out the same. Associative property of vector addition. Again, I wish they said a vector addition would be, if you add U plus V first and then add W to it, the same as adding to U the sum of V plus W. And if you did these by components, this would be U1 plus V1 plus W1. This would be U1 plus V1 plus W1. Same components in the same order, everything's the same. Okay? Now, the U plus the 0 vector has to be U, and that's called the additive identity property. Okay? That's why you have to have a 0 vector so you can have this property. It has to be there for it to be a linear system. And sort of the contrast of that too is if you add a vector to its opposite, you're going to get the 0 vector. You have to have that too, and that's called the additive inverse property. That's why you have to have a 0. One reason you have to have a 0 vector. Now here's a strange one, but true. It is an associative like property of multiplication. If you're multiplying 2 scalars to a vector, you can either multiply one scalar to the product of the other scalar in the vector, or multiply the product of the 2 scalars to the vector. It is sort of an associative property of multiplication, but it's not vector multiplication, it's scalar multiplication, okay, to a vector. And this is a distributive property of scalar addition over vector multiplication, okay? So C plus D, 2 scalars added together, times a vector U would be the same as C times U plus D times U, okay? And again, you can do it by components, and you see all these work out the same way. This is scalar multiplication over vector addition. This is scalar addition over vector multiplication, scalar multiplication over vector addition, C times U plus C times V. Okay? And again, you can do it by components, and you see it rounds up exactly this. Okay? Both of those are different forms of distributive properties. Okay? And then the last one, 1 times a vector U is still the vector U. That's called the multiplicative identity element. And 0 times a vector U is going to be the 0 vector, because it's a scalar number by a vector. It's got to give you a vector answer, so it's a 0 vector. So this is the multiplicative identity element, and this is multiplication by 0. It's about the only thing I can say. This is additive identity element. This would be multiplicative identity element, and this is just, if you think about the zero product principle with a scalar and a vector. Okay. Hopefully these are exactly like you would expect them to be. The thing that we don't see here, and it's hard to see it because you don't see it, is they haven't even defined what we mean to multiply two vectors. Multiplying scalars times vectors, fine, but multiplying vectors, not there. And probably they won't be there for a little bit. Hopefully we'll get there before the end of the term. Okay. Any set of vectors with an accompanying set of scalars that satisfies those 8 properties in Theorem 11.1, just on the previous slide, that's called a vector space. I wasn't sure they were going to get to this yet. That's why it's necessary to have the 0 vector. Like I said, it almost is a contradiction of what a vector should be, but it's absolutely necessary to have, otherwise you don't have a vector space. And you need to have a vector space. The 8 properties of the vector space axioms, and this is what Emmy Noether was really famous for. So this theorem states that the set of vectors in the plane with the set of real numbers forms a vector space. Okay? That's about all we're going to do with it. If you do take linear algebra, you'll get a lot more into spaces themselves, including vector spaces. So the length of a scalar multiple, okay, sort of a combination of concepts here. If V is a vector and C is any old scalar, then the magnitude of that C, whatever that C was, multiplied by this vector V, is going to be the absolute value of the scalar times the magnitude of the vector. Okay? And here's why we have to say it that way. Length is always a positive quantity. Magnitude is always a positive quantity. If you let C be a negative number, you have to have the absolute value bars there. Because this is always a positive quantity, you have to have this. C is the absolute value of that scalar C. So you can have C being positive, negative, even 0, okay? But you have to use the absolute value there. So if you have scalar multiplication of any scalar number times the vector V, the magnitude of that resulting vector is going to be absolute value of C times the magnitude of V. Okay. In many applications of vectors, it is useful to find a unit vector that has the same direction as a given vector. This theorem tells you how to do it. Pretty straightforward. A unit vector in the direction of V, in other words, you have some vector here, V. What's the unit vector that's in that direction? Well, this is a long vector V, unit vector must be here. Same direction, but unit length of 1. But this is a really short vector V, and the unit vector may be up here. Same direction, with magnitude equal to 1. So whatever you're thinking. So how do we find that? Pretty simple. Now, only if V is a non-zero vector. If V is a 0 vector, it has no unit vector representing it, because the 0 vector can have a magnitude of 1. No multiple of it can have a magnitude of 1. So as long as V is not a 0 vector, then to get the unit vector in the direction of v. Now don't think that anytime you see u, it's going to be a unit vector. That's why I like to put the caret on top of it, because that reminds me this u is a unit vector. Okay? That would be the vector v divided by its magnitude. Vector v is a long old vector divided by its magnitude. Now you have unit length 1. Vector v is a really short one divided by a very small number, and you expand it to be the vector v, unit length. Okay? Or you could write this 1 over magnitude times the vector v. Has a length of 1, same direction as v. Same direction v because you're multiplying by a scalar, a positive scalar number, so it doesn't change the direction of it, but it does either scales up or scales down the length to make it a unit vector. Okay. Now, from this theorem, u is called the unit vector in the direction of v. The process of multiplying v by 1 over the magnitude of v to get a unit vector is called the normalization of v. Now this kind of drives me a little nuts. It's not going to be much longer. It's going to be in Cal 3, I think. Do we do normal vectors in here? Tangent vectors? Unit normal vectors? No, that's in Cal 3. So when we're talking normal, then we mean perpendicular. When we're talking about normalization, that means getting it just to the length of 1. Those have nothing really to do with each other, but they use almost the same word. Okay? Later we'll also call a normal, and this is what I was talking about with the plane. The normal to a plane is perpendicular to the plane. So there's just all sorts of ways they use that same word, and it gets a little overused. But this is called, to make it into a unit vector, is called normalizing it. Statistics and other places, they lots of times do normalization. You get everything to the same scale, basically. Okay. Generally, the length of the sum of two vectors is not equal to the sum of their lengths, right? One vector like this, another vector like this. The sum of the two vectors is generally going to be shorter than the length of the two sides of the two vectors. Sum of the lengths. Because in general they'll be less than. If they're in the same direction, then they'll be equal. But to see this, consider two vectors u and v as shown here. Here's vector u, there's vector v. This u plus v, that's the vector sum of the two vectors. The magnitude of this is less than the magnitude of this plus the magnitude of this. So the magnitude of the sum of the magnitudes is always greater than or equal to the magnitude of the sum. That's what we're getting at. It's called the triangle inequality. Now let's see if they don't express it. Here it is. If u and v are two sides of a triangle, okay, then the length of the third side is the magnitude of u plus v, okay? And the magnitude of u plus v is always going to be less than or equal to, so the magnitude of the sum of two vectors is always less than or equal to the sum of the magnitude of those two vectors, because there could be an angle in between that's not 180, not in a straight line. Now, if indeed these were same direction, then you have the equality here. If they're not the same direction, it's always going to be less. Equality only occurs when the vectors u and v have the same direction. This result is the triangle inequality. So if they're not the same direction, they're always going to be, this will be less than that. Okay. You will use this in further proofs if you get into doing lots of proofs. Okay. Seems like we ought to have an example somewhere here. Yeah, example 4 before we get to standard unit vectors. Okay. We've just gone past when we usually have a break. Does anyone need a break? I'll be glad. You do? Okay. Sorry, I got kind of carried away. I meant to ask one of you to look. So let's just, all right, back to the recording. I've gone back a few slides so we'd have room to write. Example 4 here. Find a unit vector in the direction of v. I'll write it as that unit vector in direction of v. V is a regular old vector, and v will be, I'll put the equal sign there because they do, -2, 5. Okay? And verify that the unit vector has length of 1. Okay. Now, before we waste too much time with it, could v possibly be a unit vector? What you think? What would be its magnitude? It would be 1. Should v have a unit magnitude of 1? Really? How do you do magnitude? The square root of -2 squared is 4 plus 25. Yeah. Square root of 29? Not quite 1. Okay. No way. Okay. In fact, just a little hint, sort of from the triangle inequality we just saw. If either one of these is greater than 1, there's no way the vector can be a unit vector. Okay. They would both have to be less than 1 unless one was 0 and the other was 1. That's the only way you can have. So yeah, that can't be a unit vector, so not. So we want to find u, which is a unit vector in the direction of v. So how would we do this? Pretty ugly carrot, but okay. What would that be? What was our formula? Right there. V divided by its magnitude. That's called normalizing it. Okay? Okay? So that would be what? Help me, somebody. We almost already did the math of it. 1 over the magnitude of v times the vector v. And what did we say the magnitude of v was? Second, the square root of 29 multiplied by the vector v, -2, 5. So if we do that, and that's supposed to be an angle bracket at the end, it's a pretty ugly one, that could be written as -2 over root 29, comma, 5 over root 29. Okay? Now, is that indeed a unit vector? How would we check? Find its magnitude. And what would be the magnitude of that vector? 4 over 29 plus 25 over 29, and sure enough that's 29 over 29, which is 1. Yep, that is a unit vector. So, it's a little hint. Each one of these had better be a fraction less than 1, or absolute value is less than 1, unless one of them 0 and the other one can be 1. But if you see a magnitude of either one of them, -2, nothing else is going to make that a unit vector, or 5, nothing else would make that a unit vector. So, yeah. That's it. All right. That was example 4. Okay. Then we were supposed to have done the triangle inequality. I just got ahead of, or behind myself or whatever. Now let's look at what we call the standard unit vectors. And I'm thinking all of you are familiar with these. If not, you will be soon if you take physics, right? All right. The unit unit vectors 1, 0 and 0, 1. These are two unit vectors because the magnitude of this one will be 1 squared plus 0 squared, which is 1 squared, third of that, 1. Okay. And both are standard unit vectors in the plane and are denoted by the I vector that is 1 in the first component, 0 in the second component, J vector, 0 in the first component, 1 in the second component. Okay? So if this is your plane, 1, 0, there's your I, 0, 1, there's your J. Okay? Unit vectors, so when I write them, when they write them, they just do them both. Okay? When I write them, I put a caret over those. Okay? These are your standard unit vectors. Okay? In the XY plane. Okay? One's in the X direction, one's in the Y direction. IJ alphabetically XY. These vectors can be used to represent any other vector uniquely. This is component notation, V1, V2. And if you think of that, it's V1, 0, that vector, added to the vector 0, V2. Well, this would be V1 times your I vector plus V2 times the J vector, V1I plus V2J. Back when I was first learning vectors, that's what we call component notation. I didn't ever see the angle brackets until recent years, okay? And that's what I would have called component notation. Or they just call it IJ notation or something like that, okay? The vector V, which is V1I plus V2J, called the linear combination of the standard unit vectors I and J, which you could just think of writing angle bracket V1 comma V2 angle bracket. So just like component notation, only here you actually put the components in there, the standard unit vectors in. Scalars, now notice here, these are scalar quantities. Those are the magnitudes of your how far you're going in the I direction, how far you're going in the J direction. So these are scalars, magnitudes. They're called the horizontal and vertical components of the vector V. They're components, they're not vectors, they're components of the vector. Okay? So they are scalar quantities themselves. All right, so here's, let U be a vector with initial point 2, -5, terminal point -1, 3. Okay? Let V be 2I minus J. Write each vector as a linear combination of I and J. Oh, each of these two. Okay. I was going to say that's already a linear combination of I and J, but they're talking about these two down here. So what would U be as a linear combination of I and J? What would you do first? And that's not a unit vector. It possibly could be, but it's not guaranteed to be, so I'll put a vector notation over it, not a unit vector notation. What would it be? Always easy to write it in component notation first. What would that be? U. -3, comma. Second? Okay. Is that -8? +8. Okay. Because it's always final minus initial. And the terminal is your final 3 minus a -5, that's a +8. But -1 minus a 2, that is a -3. Okay. Is that a unit vector? No. Both components are greater than 1. It can't possibly be a unit vector, okay? But they didn't ask for it to be, okay? But it did ask for you to write it as a linear combination of I and J. So how would you write that? -3I plus 8J. I like to put my carets over it. You don't have to if you don't want to. Okay, how would you write W as a vector? Now, any way you think this might be a unit vector? Well, let's just see it, if perhaps it is. Okay, so what would that be? Seven. Okay, I'm not sure how you got that. Tell me how you got that. All right, I won't. Here's U, there's V. Two times U, first component, that would be 2 times negative 3 is negative 6 minus, and you may be right, I wasn't even looking at this. That's negative 6 minus a 3 times 2. What would that be? All right, we don't have to do it in your head. Let's write it out. This would be 2 times negative 3i plus 8j minus 3 times 2i minus j. Okay. What would this one be? Negative 6i 16j minus 6i plus 3j. Combine components, and what do you get? Negative 12i, second, plus 19j. Okay, let's see how the book did it. First, negative 3i plus 8j is your u, and negative 12i plus 19j is your w. Okay. Any questions on that? So you don't have to do them all in your head. I thought, as fast as y'all were doing them before, I thought I was slowing you down, but good way to do it. Or you can write them off in component notation, do that, and then get back to this. It doesn't really matter. A little more writing this way, but maybe a little easier to see. I don't know. Okay? All right, to erase. All right, let's see how they do the first part. Well, they write U as Q, which they're going to let that be your terminal point, Q1 to negative 1 minus 2. Okay? That gives you your minus 3 as your first component, and then 3 minus your minus 5 is 8. So that would be negative 1 minus 2, comma, 3 minus of minus 5, which is negative 3, comma, 8, which in, what do they call it, linear combination of unit vectors is minus 3i plus 8j. All right. And the B part is then take that answer, combine it with the V that you had up there, given that way, and in this linear combination, and see what you get. 2 times this would be 2 times this vector here, minus 3 times this vector here. Okay, exactly like we read it. And that would be minus 6i plus 16j minus 6i plus 3j, and then combine like components, not like terms, but like components, negative 12i plus 19j. Does that make sense? Pretty straightforward, right? I know y'all are hating this is going to be on your last test, right? All right, good deal. Okay, let's see where we are now. All right. Looks like they skipped example 6, so let's go back and do example 6. Writing a vector of given magnitude and direction. The vector v has a magnitude of 3. Think it's a unit vector? No, it's not. It'd have to have a magnitude of 1 to be a unit vector, okay? And makes an angle of 30 degrees, or pi 6, with the positive x-axis. Pi 6 radians. Write v as a linear combination of the unit vectors I and j. Okay? So I'm going to say that's my vector v. And this is length 1, and length 1, so that has a magnitude of 3. Okay? It says, write that vector v as a linear combination of the vectors I, which would be something about like this, and j, which would be something about like that. Okay? How in the world do we do this? Absolutely. How would you use trig to find it? Okay. Did I have here that v sub x, which is a component in the horizontal direction, is equal to 3, which is your magnitude of v, times the cosine of this angle. You prefer degrees or radians? I don't really care too much. Second? Use degrees. Okay, 30 degrees. My hearing's bad. Okay, does anyone happen to know what the cosine of 30 degrees is? Root 3 over 2. So this will be 3 root 3 over 6. That's your v sub x. How about your v sub y? 3 times the sine of 30 degrees, which would be, second? 3 halves. Perfect. So it says write v as a linear combination of the unit vectors this. So your vector v would be, let's see, how in the world did I get that? I don't know. That's a 2 down there, not a 6. I don't know where the 6 came from. Okay. All right. 3 root 3. No. Yeah, that's right. 3 root 3 over 2i plus 3 halves j. All right. Think that's a unit vector? No, it can't possibly be. This thing's way bigger than 1. That's bigger than 1, so it's not. No way. But that's your vector written as a, so 3 root 3i plus 3 over 2. 3 root 3 over 2i plus 3 over 2j. Okay? And by the way, even though they haven't said it yet, this is true for any. If you know any vector v, the magnitude of v, and you know its direction, again, relative to the positive x-axis, okay, then that vector v can be written as magnitude of v cosine theta in the I direction plus magnitude of v sine theta in the y direction. I wish I could have planned a little better. You can, I mean, that's a given. Okay, so if you know the angle theta, you know the magnitude, or you can calculate the magnitude, you got it. Okay, now we get to all right. As we were saying earlier, the very beginning of this chapter, section, vectors have many applications in physics and engineering. One example is a force. A force is a vector quantity. It has a direction and it has a magnitude. Vector can be used to represent a force because force has both magnitude and direction. Boy, did I just say that. If two or more forces are acting on an object, then the resultant force on the object is the vector sum of the vector forces, not some sort of scalar sum. This is vector, a triangle inequality. Let me give you just a really dumb example of this. When we first moved into the house where we currently live, the previous owners had just let trees grow up wherever they wanted to grow, and we liked the fact that it had trees, but some of the trees were really sorry looking. And there were two scraggly little pine trees that were trying to make their way through the canopy of some really big oak and pecan trees. And they were crooked, and because they were trying to find their way to the sun, and very thin and scrawny looking, just really ugly trees, okay? And we hate cutting trees, but they just had no future under those big canopies. So my father-in-law came down from Huntsville with his son-in-law, my brother-in-law, and we were going to take down those two trees. But we didn't want them going toward the house or toward anything else. We wanted to sort of make them fall and land the way we wanted them to. And they were pretty tall trees. They were scrawny, but they were tall. So they brought with them, a good line that we threw as far up as we could. Finally got it wrapped around one of the lower limbs, which was way up there. So here we had the two ends of the rope, okay? Now, to get the maximum force to get it to pull the way we wanted to, my brother-in-law and I could have pulled in the same direction exactly where we wanted the tree to fall, and while my father-in-law did the honors with the chainsaw. Would that have been a wise idea? No, they would have fallen straight on top of us, right? So what we did, we got at an angle, okay? And we tried to pull with equal forces. Now, did we have as much force doing that way? No, because he could pull with a certain force this way, I could pull with a certain force that way. I think vice versa, but it doesn't really matter. We both had components in this direction, which was good, but we also had components like this, which were opposite each other. So we weren't pulling with as much force, but the sum of the forces were in this direction, which split the difference between the two of us, at least approximately, so the tree would fall between us, which is exactly where we wanted it to go. Now, of course, that makes perfect sense. You didn't have to think physics, but that was exactly what was going on here. Do any of you live sort of out in the country-ish, and you see power lines, and you see, especially, we see this up in Minster County where the roads kind of go like this, power lines are sort of going like this too, and every time the power line makes a turn, they have to have a guy wire over here, because otherwise, the force of the power lines would be pulling that power pole over, and they would pull it over. So they have to have a vector in that direction, sort of counter exactly this, to create the force, to counteract the force in this direction and that direction to pull that way. We call them the guy wires, okay, as opposed to the gal wires. No. Okay, so all representing forces, okay? So the two or more forces are acting on an object. The resultant force is the vector sum, not the scalar sum of the two vector forces. Okay. Here's an example of this. Two tugboats are pushing an ocean liner. Okay, I won't say which line it would be under. Okay, as shown in this figure, each boat is exerting a force of 400 pounds. Do you think the force being exerted on the ocean liner is 800 pounds? Does that make sense? No, because they are pushing at an angle other than the same, okay? This one pushing at an angle of 20 degrees with horizontal, below 20 degrees, this one 20 degrees above the horizontal. So there's no way the sum of these two forces can be 800, even though each of the forces is 400. So what is the resultant force on the ocean liner? Okay, because these two are exactly the same, and the angles are exactly the same, but in opposite directions, the vertical components exactly cancel each other out. So you only have the sum of the two horizontal components. These two exactly cancel each other out, because sine of negative 20 is exactly the opposite of sine of 20, and so those are going to add to 0. But because cosine is an even function, the cosine of minus 20 is exactly the same as cosine of 20. Okay, so you can do that. So that's the only thing we have to do is add those two together. Now I don't have a calculator on me, and I can't do this one in my head, so someone do. 400 times the cosine of negative 20, or 20, I don't care which you do. Easier probably to do 20. Be sure you're in degree mode now. If you're in radian mode, you're going to get wacko answer. 400 times the cosine of 20 degrees would be something less than 400 for sure. What is it? 3?
Well, I went ahead and added them both.
Oh, you did.
Sorry, and it's 751.
751. So these two would be the sum of these two together, 751 pounds. Not 800. Close, because it's a pretty small angle there, but not 800. Okay. Make sense? All right, good deal. Let's see what they got in the book. They got 752 pounds, okay? They must have rounded differently from what you did. Okay. Any of you civil engineers or pre-civil engineers? Oh, you are. Done any surveying yet? Huh? You're about to, okay. You're going to be dealing with bearings out the ears now, right? Okay. Those are vector quantities, okay? Let's see, they may actually, let's see how they do this problem first. Okay, using the figure that we saw, you can represent the forces exerted by the first and second tugboats. Add the first one, 400 times, and this is, okay, 400 is the magnitude of the vector, and the x component is cosine 20 degrees, y component sine 20 degrees, just like we did an earlier problem, okay? So this would be 400 cosine 20i plus 400 sine 20j. That's tugboat 1. Tugboat 2, 400, still the magnitude of the force, cosine minus 20, comma, sine minus 20. Those, by the way, are the unit vectors in that direction. That would be 400 cosine 20. Okay. Now notice what they did here. They said because cosine is an even function, cosine of minus 20 is equal to cosine of 20. But because sine is an odd function, sine of minus 20 is minus the sine of 20. So they interjected the minus sign here because of the oddness of sine, did away with it here because of the evenness of cosine. Those up there were both positives, so it didn't really matter. Okay, so then what you do, add components. So you're adding these two components, but notice these two components exactly cancel each other out. One's positive, one's negative, exactly cancel. So you just have twice the 400 times the cosine of 20. Okay? So they added, well, they went into gory detail here. They did, this is the I, that's the J, that's the I, which is exactly the same. That's the J, which is exactly the opposite. So when you added them together, you get 800 cosine I, cosine 20I, 0 in the J direction, which makes sense if you think about it, and they got 752 pounds in the I direction. So the resulting force of the ocean liner is about 752 pounds in the direction of the positive x-axis. Okay. All right. So here's what I was just about to say. In surveying and in navigation, a bearing is a direction that measures the acute angle that a path or a line of sight makes with a fixed north-south line. So you can either think of north-south as being actually north-south, or on a map, north being up and south being down, however you want to do it. We're talking about an acute angle. What does it mean by that? Acute, less than 90 degrees. Okay? So, an acute angle that a path or a line of sight makes with a fixed north-south line. In air navigation, bearings are measured in degrees clockwise from north. Okay, so if north is this way, clockwise, which is exactly opposite of what we do, in many ways opposite of what we do in trigonometry, which we take the positive x-axis as being our basis and go counterclockwise. So in that air navigation, bearings are measured in degrees clockwise from north. So this would be 0 degrees, 20, 40, 60, 80, 90, north. Okay. We'll get into how to name that later. But then if we're only dealing with acute angles, when you get down here, you measure it from south. Okay, we'll get it. Whoa! That's all they did. Okay? Then they give the example. Okay? So you can go to larsoncalculus.com for an interactive version of example 8. Here's what it is. Airplane is traveling at a fixed altitude with negligible wind factor. The airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees. Okay? So if this is your north, that's your east-west, and this would be south, of course. 330 degrees would be all the way around here until you were 30 degrees short of 360. So there is 330 degrees. Okay? Now, with a speed of 500 miles per hour, so I'll just assume this length here represents 500 miles per hour. Okay? As the airplane reaches a certain point, it encounters wind with a velocity of 70 miles per hour in the direction of, now here's how they show you the direction, north 45 degrees east. That means look to the north, but go 45 degrees toward the east. Okay? So this would be north 45 degrees east in the eastern direction from north. Okay? That's the direction of the wind, and that's the magnitude here is 75 miles per hour. Was it 75 or 70? 70, I can't read. Okay. 70 miles per hour. Now, mine probably are not drawn to scale, so don't even expect them to be. 70 miles per hour. That's the wind. Okay? Control and figure. What is the resultant speed and direction of the airplane? Okay. Now, I think I know how they do it, and it's perfectly fine to do it that way, but you can also do it just based on this. You can take north, east, southwest, whatever you want to do, and deal with your components that way. I have a feeling they're going to do everything in X, Y, which is perfectly fine to do, but it's a little bit extra work in this problem, but it's still pretty easy. Okay? So do you want to do it north, south, east, west, or X, Y? I really don't care too much. You've already paid your money, take your choice. X, Y, or north, south, east, west. XY. Okay, let's do it XY. So, the plane speed and direction, if you're doing XY, the X would be a minus, okay? Now, if that's 330, that means this is 30 degrees, right? So that would be in the minus X direction, and what would be the magnitude of the X component here?
500 cosine 30 degrees.
Say again?
500 cosine 30 degrees.
Okay, cosine 30 degrees? Okay. Okay, I know what you're doing, and I probably should have then done it the other way. We probably should be working with that angle. That's our reference angle. So what would that be?
60 degrees.
That would be 60 degrees. Okay, so let's hit it again then.
So it goes 500 cosine 60.
Okay, let's call this V sub P for the velocity of the plane is minus 500 times the cosine of 60 degrees. Okay, in the I direction. Okay, how about in the J direction?
Is it still minus 500 for the magnitude?
Okay, did I hear a 500 in there? Okay, times the sine of, if we're using 60, so let's stay with 60 degrees. Okay, now, anyone know what the cosine of 60 is? 1/2. So 1/2 of minus 500 is minus 250, and this is in miles per hour? Yeah, miles per hour. 250 miles per hour in the I direction, and this would be plus, anyone know what the is 250 times the square root of 3 in the J direction. Okay, that's the velocity of the plane. Let's do the velocity of the wind. Any ideas?
So the I direction is going to be 70 cosine 45 degrees.
Okay, 70 times the cosine of 45 degrees in the I direction plus
70
sine of 45 degrees in the J direction. Okay, and going northeast, you're in the first quadrant, both are positive, so everything's fine there. Anyone know what that would be? Cosine of 45? Root 2 over 2, so this would be 35 times root 2 miles per hour in the I direction, and this would be 35 root 2 miles per hour in the J direction. And then just add these two together. So nicely said, but poorly done. Your velocity with respect to the Earth, so I'm going to call that this. Technically, these should have been vectors. Okay, they are vectors. This will be 35 root 2 minus 250 in the I direction plus 35 root 2 plus 250 root 3 in the J direction. Now, pull out your calculators and find out what numbers those are approximately. That would be the vector quantity of your velocity, which does not answer either question we had. Okay, but it's a good thing to know. Negative 225. Second. 200.5. Okay. 200.5 in the I direction, and this would be 251, you said?
51.5.
Whoa.
I got 482.
Yeah, that's going to have to be a bigger number than that. Both of them are positive.
408.
Second?
408.
Or if you want to round up to 42.
Okay, I still couldn't hear. 482? Is that what someone said?
482.5.
483.5? Or 2.5?
482.
482.
Yes.
Okay, we'll leave it there in the J direction. Now, that does not answer either question, because the questions are, what are the resultant speed and direction of the airplane? What is the speed? That's the magnitude of your velocity. So the speed is equal to the square root of, and when you're squaring it, you can lose the sign, 200.5 squared plus 482 squared, or at least approximately this. What will that give us? They did 482.5, by the way, so if you want to get the same answer they did in the back of in the book, you can do that. Okay. .523 approximately miles per hour. Does that sort of make sense? Well, the plane was going up here at a pretty high rate of speed. The wind, pretty high rate of speed, but considerably less than the plane. So it's going to be greater in the Y direction, a little bit less than you would expect in the X direction, but still, this is 45 this way and 60 that way, so you, and 30 this way. So yeah, that seems to make sense, and they got 522.5, which is 523. Yeah, that's good. Okay, but the other question is, what is the direction of the airplane? That is its speed over ground. What is the direction? Actual direction now, not the way he thinks he's pointing, but his actual direction. What would you do there? Yeah, the angle theta that he's actually going in is going to be the inverse tangent of the y component 482.5 over the x component 200.5. Okay, and it could be a plus or minus of this. We're going to have to see. I mean, this may not give you the actual number, but it'll get you in the ballpark. What does that give you? 67. Give me 0.4 degrees. Now, the way we are doing it, that would have been y component, x component. That would have been an angle over here. Okay? That's not how they measure angles in air navigation. They measure around like this. So that would be your 270 plus that. So, where did I write it down? Yeah, there it is. So let's do 270 plus that. 67.4. And that would be 337.4 degrees. Okay? But, oh, this drives me nuts. They say, but with respect to the positive x-axis, that's not how you measure this, but so let's go back and do the other. So that was our 67, so what you would do is subtract that from 180. So 180 minus 67.4. 112.6 degrees from the positive x-axis. But that's not how they measure it in air navigation, so a little nuts, but okay. So there's 11.1. Homework exercises here would include, number 3 should be at calcchat.com. 5 or 7 are both at CalcChat, 5's at CalcView. Any of the odds 9 through 15, they're all at CalcChat, 11's at CalcView. Any of the, do 17 is at CalcChat. 19 to 23, they're all at CalcChat, 21's at CalcView, 25's at CalcChat, 27's at CalcChat and CalcView. Any of the odds 29 to 33, they're all at CalcChat. 35 or 37 are both at CalcChat, but 35's at CalcView. 39 or 41 are both at CalcChat. 43's at CalcChat. Either 45 or 47, they're both at CalcChat. 47's at CalcView. 49 or 51, both at CalcChat. 49's at CalcView. 53 or 55, they're both at CalcChat. You can explore doing 57 and or 59 if you choose. That's up to you. They should be at CalcChat. 61 to 65, they should all be at CalcChat. 67 to 71, they should all be at CalcChat. 73 should be at CalcChat. 75 and or 77 should both be at CalcChat. 79's at CalcChat. 81's at CalcChat. And 83's at CalcChat. 85 to 93 are true-false. They should all be at CalcChat. 95's a proof. If you want to do it, that's a CalcChat. 97's a geometry problem at CalcChat. And 99's a vector problem at CalcChat. All right. That's 11.1. Let's move on to 11.2. Well, my computer's doing weird things, but that's nothing new. 11.2. It will get here in a few minutes. There we go. And let's go from current slide. Still, chapter 11 is vectors in the geometry of space. 11.2 is space coordinates and vectors in space. 11.1, plane, 2 component systems. 11.2, space, 3 component systems. That's just about it, okay, as a difference. We'll understand, objectives here is to understand the 3-dimensional rectangular coordinate system, and we'll analyze vectors in space. All right, so let's talk about coordinates in space. Before extending the concept of vectors to 3 dimensions, you must first be able to identify points on a 3-dimensional coordinate system. Okay? You can construct this system by passing a z-axis perpendicular to both the x and the y-axis at the origin as shown here. So let's just use this corner of the room as my z-axis here. This will be my x-axis. That will be my y-axis. Now, why did I choose that way? Right-hand rule. If you point your fingers in the direction of your right hand, fingers in the direction of the positive x-axis, bend them 90 degrees, the right hand, that would be the positive y direction. Your thumb is in the positive z direction. Okay? It's called the right-hand rule. Okay? So, taken as pairs, as opposed to apples, the axes determine the 3 coordinate planes. The xy plane would be the floor down here. The xz plane would be this wall over here, and the yz plane would be this wall here. Now, of course, we're just in one octant here, okay? On the other side of the wall here, you have, the plane. Outside here you have, and down below you have, so there's 8 octaves. We're just in one. But this shows all 8. We're in this one here, positive X, positive Y, positive Z. From here up. From here down on the floor below us would be the plane, the area of space down there, and then one out there would be that one over there would be this one, and down all around. Okay. Now, these 3 coordinate planes separate 3 space, that's 3-dimensional space, into 8 octaves that I was just talking about. The first octave is the one for which all 3 coordinates are positive. That's where we're living right now. In this 3-dimensional system, a point P in space is determined by an ordered triplet, not an ordered pair anymore, ordered triplet. Okay, X would be how far from the YZ plane you are. Okay, the Y coordinate would be how far you are from the XZ plane, and the Z coordinate how far you are from the XY plane. Okay. So let's say we have a point right up here. How about that thing right there? So we could measure approximately 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, maybe about 12 feet in the positive x-axis. We'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, about 10 in the positive y-axis. And this is going to be harder to do because these are 8-inch blocks. So let's just say that's 10 feet tall. So positive 10 in the Z direction. So that would be that point right up there, that device there. Ordered triplets. Now notice both words are important. Triple, meaning there's 3 components to it, 3 coordinates to it, not components, coordinates. Ordered, the order matters. This is always with respect to the X. Second is always with respect to Y. Third is always. That's what the order means. For X, Y, and Z are as follows. X is the directed distance from the YZ plane. Y is the directed distance from the XZ plane. Z is the directed distance from the XY plane. Okay? Several points are shown here. And this is a mess to draw and to interpret, because you're drawing a 3-dimensional system on a 2-dimensional plane here, so it's a mess. Okay, let's take this point right here. We're plus 3 at X. Here's positive X, positive Y, positive Z. Plus 3 on X, plus 3 on Y, but down 2 here. Okay, with the construction lines here, it's kind of making sense. Kind of making sense. Kind of, because here, notice each of the tick marks here is 1 in the X direction, but each tick mark here is 2 in the Y direction. And that's just because of perspective here. This is coming more out at you. That one's going, you have to really be careful, because I was going to say, this looks a lot shorter than that to me, and it is. Okay, the Z down 2, so that's okay. Over here, you're 1 positive on X, 6 positive on Y, 2, 4, 6, and 0 on Z, so you're in the XY plane. This one over here is minus 1, 2, 3, no, 1, 2 on the X, plus, looks like about 5 on the Y, and plus 4 on the Z. Okay? And over here, back here, you're positive 2 on the X, minus 5 on the Y, and plus 2 on the Z. Now, without those construction lines, it's just possible to tell. Because all these points are on the same plane, the actual plane, but you have to have the perspective here to get about where they meet in 3 dimensions. Because you're trying to project 3 dimensions onto a 2-dimensional plane. Okay, but that's how you do it. It's not a fun task. Okay, the 3-dimensional coordinate system can either have a right-handed or left-handed orientation. Now, I gave it with the fingers. I didn't give you the fingers, but I gave it with the fingers. To determine the orientation of this system, imagine you're standing at the origin with your arms pointing in the direction of the positive X and Y axis, then the positive Z axis pointing up. Your right hand would be X, left hand Y, your head would be pointing up. That's how they say it. I like to use hand. That's how I always learn. So the system is right-handed or left-handed, depending on which hand points along the x-axis. In this text, we'll always work with right-handed system. Okay? So don't mess with left-handed. So I'm left-handed. Okay. Many of the formulas established for two-dimensional coordinate systems can be extended basically seamlessly in 3 dimensions. For instance, to find the distance between 2 points in space, use the Pythagorean theorem twice. Okay? So you do the first one, and I think this figure leaves a lot to be desired. Here's point P and there's point Q. Okay? To get the distance from P, the projection of P onto the XY plane and the projection of Q onto the XY plane, just basically projecting down there, and that would be the difference in X's squared plus difference in Y squared, just like we had before. Okay? Now, that would be the distance from here. Okay? The distance Z here, to get the D, the actual distance between these 2 points, you'd use this one you just came up with, which was the distance of the projection of PQ onto the XY plane with the Z component here, which is the magnitude of the difference between Z here. So it would be this one here, square root of that, plus, and square root of this squared, which is what you got there, plus the square root of this squared, which would be, let's show it here, the square root of Z2 minus Z1 squared, and then put them all under the square root, and you've got exactly the extension here. By doing this, you'll obtain the formula for the distance between 2 points, x1, y1, z1, and x2, y2, z2. That distance would be the difference of x's squared plus the difference of y squared plus the difference of z squared. Okay. Now, does it matter which points you put first? No, because your difference is being squared. That'll be a positive quantity, that'll be a positive quantity, that'll be a positive quantity. You're adding 3 positive quantities, it will be positive. Taking a square root will be a positive. So it really doesn't matter the order. You typically do it this way, but it really doesn't matter because you're squaring the difference. Whichever one you put first or second, it's going to be the same once you square it. Okay, so let's do this one. Find the distance between these 2 points. 2, -1, 3, and 1, 0, -2. So let me get my pen set up. Distance is equal to the square root of what? Second? 2 minus 1, that is what I heard. Yay or nay? Squared plus minus 0 squared, that's fine. Okay, 3 minus a minus 2. Now, did it matter which one I did first? No, it didn't, because this will be the square root of 1 plus 1 plus 5 squared, which is 25. So this will be the square root of 27. I hope. Yes. And then they simplified this in some senses to 3 root 3. Perfect. Yeah. Perfect square hiding in 27 is lurking in 27 is 9. 9 times 3, square root of 9 is 3, so it's 3 root 3. Okay. Now, let's just see how they do it. It's perfectly fine, but I don't think it'll be much different. They just reversed them, okay? They did, which technically by their formula is 1 minus 2, which is the minus 1 squared, plus 0 minus the minus 1, which is 0 plus 1 squared, plus a negative 2 minus 3 squared, negative 5 squared. But guess what? That gives you square root of 1 plus 25, which is square root of 27. So it really doesn't matter the order you do those, okay? And that's 3 root 3. Okay, now, there's a couple more definitions here. A sphere with a center at x0, y0, z0, and a radius r, and remember a sphere from the center, the exterior is always the same distance from that center, is defined to be the set of all points x, y, z, such that the distance between x, y, z and the center is always r. You can use the distance formula to find the standard equation of a sphere of radius r centered at that, and let's do it. Okay? So what would that come out being? What's the distance between those 2 points? X minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to r. Is r. I mean, we just did this thing. The distance between these 2 points, there it is that's equal r. Oh, where did I get 5? Okay. I do not know, okay? I guess that was my last problem or somewhere, I don't know, is r, okay? Okay, now that's not quite a standard equation of a sphere. What we would do is square both sides. And that gives you x minus x0 squared plus y minus y0 squared plus z minus z0 squared is equal to r squared. That's still not quite standard, I don't think. Maybe the book counts it. I like to go on and divide both sides by r squared. So that would give me x minus x0 squared over r squared plus y minus y0 squared over r squared plus z minus z0 squared over r squared is equal to 1. I don't know if they count that as standard or not. No, they count this one right here without the dividing by r squared. Okay, and that is the equation of a sphere. Now, here's what makes it a sphere. All the coefficients are the same. In this case, 1, 1, 1, 1 of your squared terms. They could be 7, 7, 7. It doesn't matter. Okay. Now, the second thing is they're all squared. Okay. That is required too. And if you wrote it in the way I did, you see still the coefficients the same. 1 over r squared, 1 over r squared, 1 over r squared of the squared terms. Okay. With pluses, oh, the other thing, pluses in between all of them. Oh my goodness, have we done it? Sorry about that. I was getting carried away. Okay, we've still got to do our midpoint formula, which I think is the next thing. So we will start right here next time. Okay. All right, good deal. We really didn't get too much into this section. I think you can do 5 or 7, they're both at Calc Chat. 9 or 11, they're both at Calc Chat. 9's at Calc View. We'll stop there and we'll do the rest of them later. Okay, good deal. All right, good deal, folks. We'll see you on Wednesday. I will try, hopefully, to have your test ready on Wednesday. If not, it's not going to be that bad of a test. So even if you get it Monday, I think you'll have plenty of time to get it done Tuesday, Wednesday, or Thursday, because there's no more classes after Monday. Do any of you have Tuesday, Thursday classes? Okay, you will have class on Tuesday, but possibly some may be giving finals that day, but yeah, you'll have plenty of time to work. Yes.
And what about the final?
That's right. That will be the final that I give you, either Wednesday or Monday, whichever day I have to get it ready. That will be your final, and get it into me by Thursday, sometime Thursday. And I leave this campus about 4:15 on Thursday. So if you're going to bring it here by 4:15 on Thursday of next week, and if you're going to bring it to the Birmingham East Campus in the nursing building, room 214, then I'll be there until at least 6:30. So you've got a little more time. But we'll talk about that next week. Well, that's another day. Good deal.